So let me introduce Dr. LaHaye or Nicholas. Nick, we call him Nick. So he is a data scientist at NASA's Jet Propulsion Laboratory at Pasadena, California. As a member of the Machine Learning and Instrument Autonomy Group, he supports active and future missions as well as application-driven research that aims to aid researchers and decision makers. Currently, he leads an effort to leverage self-supervised models and multi-sensor datasets to segment and track object instances like wildfire fronts, plumes, harmful algae blooms, palm oil farms in low and no label environments. This effort strives to integrate both on the ground research and decision making application as well as next generation onboard retrieval capabilities. He also currently works on data driven retrieval techniques for 3D cloud, tomography, and data driven hydrological retrieval and validation techniques for Sentinel-6 and the SWAT. Previously, he split his time between research and the development, generalization, and maintenance of pieces of the operational science data systems like missions like MISR, JSON-3, SWAT, as well as airborne programs like AIR, MSPI, and High TES. With that, Nick, please take it away.
Yeah. Okay. Yeah, no, we do. Okay. Hi, everybody. Thank you for coming. So today I'm gonna kind of briefly go over kind of the reason behind the desire to evaluate the encoder complexity, kind of what our use case is in the fire and smoke domain, and then talk about the kind of framework that we've developed and show some kind of initial results and kind of the path forward that we're looking at. Okay, so kind of the overall background, right? There's a whole bunch of instruments, both from NASA and from other global organizations that are Earth orbiting, airborne, and they have varying spatial, spectral, temporal resolutions, varying specialties. But the overarching goal has been for a long time to be able to use these collectively to observe and retrieve information from various Earth systems and various geophysical phenomena and things like that. So that's kind of a large task to tackle. So a small piece of that overarching goal that we aim to tackle was the capability to be able to segment geophysical objects and then track them across instances of the same input data set and then across input data sets from different streams. So, you're tracking a smoke plume from one instrument and you want to be able to say that with some certainty that you're still looking at the same smoke plume across the data set from another instrument. And with that, we started with the static segmentation portion of that. And that's going to be kind of the majority of the talk. The temporal tracking portion is another piece, which I'll briefly mention here, but it's kind of currently ongoing work. So for the static segmentation portion, we've developed this capability that there's again all these instruments. There's limited labels or no labels in lots of cases for a lot of these problems, and we want to be able to leverage the machine learning techniques to do this stuff and also keep subject matter experts in the loop. So we want a way to employ subject matter expert knowledge without having to levy extreme amounts of labor on them, pre-analysis. So with that, we're using self-supervised encoders and self-supervised segmentation layers to generate per scene segmentation maps. And then we have the capability to, ask the subject matter expert to coarsely identify geophysical objects of interest in a couple of training scenes, and we'll look at how that maps into like large scale context assignment. Our like overall kind of vision for a larger architecture set looks like this diagram here on the left. These instruments are again specialized, different spectral resolutions, different polarization channels. Some of them have a sweeping gimbal, most of them are static, pointing, at some specific pointing angle. But we really want to be able to leverage the specialization of each of these. And from our perspective, it makes the most sense to have encodings that kind of can interplay with each other, but are themselves distinct across these different instrument sets, right? Some of these things, so some of these are showing hyperspectral instrumentations. This one here is a scene from a SAR, polarized SAR instrument, right? So really, we should be able to leverage these data sets kind of separate and distinct by themselves, and then, combine them or look across them, when desired. And then, there's also some temporal aspects, as I mentioned, kind of downstream of that, but not everything has a temporal component to it. So, we want to be able to look at just spatial and then also spatiotemporal, and then take this information and leverage it for further downstream retrieval. So we've segmented the smoke plume, how can we leverage that to minimize the compute for, say, aerosol optical depth retrievals or aerosol type retrievals, or fire radiative power for the active fire front, things like that. Yeah, so we have the encoder portion, and then we have this self-supervised segmentation. So initially we started with just basic unsupervised clustering. In recent times, we've transitioned into deep clustering to do this self-supervised segmentation. And kind of a novel piece that we've done here is we've mimicked the tree structure of traditional clustering in the neural network architecture. So we can have different uh, complexity layers of the segmentation. So let's say you want to dig deep into, what is being distinguished between in a fire front, right? You can look at, the coarse segmentation, which I'll show in a bit, and then you can also kind of go in and see what's being identified as distinct and separate subclasses of that fire front. Yeah, so kind of went over all this stuff. So we have our representation learning from our encoders. We have our clustered scenes. So none of those pieces have labels associated with them. And then, as I mentioned, the subject matter experts can come in and generate these basically mappings between coarse identifications of the areas of interest and the associated context-free labels that exist in the initial output from the models. So this is a kind of very rough sketch of how that might work. Typically, this is done in a GIS for now. There could be some kind of specialized interface in the future. But yeah, you can identify areas that are smoke, fire, background, and then the low certainty areas can just be left blank, right? It's not being fed into the model directly, so there's no need to actually identify every single pixel. And there's no need to identify it like extremely precisely. Covering the majority of the area in our experience has allowed us to be able to generate these mappings with good performance associated. And it can be done, kind of iteratively. So you identify maybe some areas that have been lacking over your initial mapping, and you can go back in and adjust these coarse polygons to maybe fix like areas where maybe you're misidentifying sun glint over water, which is what's in this scene here versus smoke, things like that. What you end up getting at the back end. So these images here are zooms in on the context-free segmentation over a full scene. So you can kind of see some things distinguished here. These are reference images, pseudo-colored of fire fronts, two separate fire fronts from a wildfire campaign. So you can kind of see those are being separated out in both of the images. And then the image directly to the right in the center of the lower row is the extraction of the labels of interest. So this case is Firefront. So there's a subset of these labels that are directly mapping to Firefront across all of the scenes in the training set. And then we currently are generating binarized and contoured segmentations, but the model does output certainties. So we'd like to be able to, pass on that certainty associated with the labels that we're generating, to kind of provide better analysis and better kind of downstream use of the product. As you can see in these two cases, the redder and brighter the pixel is in these bands. These are thermal bands. The higher the intensity of the fire. And so there's different colors that are mapping to different intensities on these fire fronts. We're identifying the brightest areas of the fire all the way to the kind of smoldering areas outside of those high intensity pieces. Another kind of valuable asset to this segmentation approach is that we have the embedding information that comes out of the encoder, but now we also have spatial distribution of these labels that come out of the deep clustering layers as well. So it's another piece of information that we can tack on as part of a signature that we can leverage to track things over time. So we have the embedding, we have the spatial distribution of the clusters, and then we also have like shape information of the overall object we're trying to track over these data sets. And initial, like very small test cases, we found that this is beneficial relative to just using the embedding on its own. We've looked at this approach over various scales. We're finalizing a paper for evaluation over the FireX AQ 2019 campaign. So it was a campaign, joint NOAA, NASA, a bunch of airborne instruments, and passes over a couple fires: the Williams Flats Fire in Washington, the Sheridan Fire in Arizona, a few other ones, and then the airborne instruments had coordinated their scenes with overpasses from polar orbiting instruments, and you have geostationary instruments as well. So we can really get a good glimpse at varying spatial, spectral, temporal resolutions, and how these instruments interplay, and how we can leverage the data collectively and get like these tiered views of these different systems. So yeah, let's see. So top right here is two different scenes. So one from two instruments aboard the same orbital platform, Terra, is Miser and Modus. Miser is a 9-angle camera with 4 spectral bands per camera, and each of the 9 cameras points at a different angle. One is at nadir, pointing directly down, and the other 8 kind of go forward and aft at higher levels of oblique angles. And then these images here at the bottom of this top right panel are from 2 different instruments on different airborne platforms. So taking imagery of the same fire from different airborne platforms. And obviously the coverage is slightly different here. We have the 2 images overlaid. And one has 38 spectral bands. It's actually the kind of airborne simulator for Modus. And then one has 50 spectral bands. So demonstrating various capabilities when these instruments are either always together, right, like on a polar orbiting platform, or whether they take images in a relatively close spatiotemporal area, demonstrating the ability to be able to kind of fuse the data sets together when appropriate. And then we also have, demonstrations of using the instrumentation separately. And then bottom left here, we're gonna go kind of out of order. This is data from, again, top row is master, the same instrument that I mentioned in the fusion case, just by itself over the Williams Flat Fire, and then EMOS by itself. Ermisby, which is it has a sweeping gimbal, so we have this different kind of data set here where instead of just kind of having the instrument fly over when the aircraft fly over the instrument static, we have the instrument actually sweeping and getting different levels of aerosol column, different thicknesses of aerosol column within the data as the gimbal sweeps. And then at the bottom here, we have geostationary GO 17. So it stays in a static position relative to the Earth as it orbits. Lower spatial resolution, but higher temporal resolution. Right, and in all these cases, I have some tables below that show some metrics, but we have pretty good performance for fire and smoke. And then, porting over to other areas across the globe. So top left is geostationary instrumentation over the North and South Korea. We have the ability to identify this kind of fire, smoke, and then in this case, there was also a yellow dust plume coming in off the coast that we were able to identify here. Yeah. So all this to say, we have this framework currently kind of for these baseline evaluations. We're using very simple encoders. So two-layer deep belief networks. So stacked restricted Boltzmann machines. Nothing complex, nothing kind of state of the art about them. But the benefit is that A, you were able to train them in a self-supervised way before kind of this latest explosion of self-supervised techniques. And B, they only have like the ones we're using only have about 2.4 million parameters, which is small relative to some of these models coming out that have hundreds of millions and even billions of parameters. So it's an approach that can be scaled and can be leveraged in places where maybe you don't have the super compute level of resources. But recognizing that when these methods get deployed, there are going to be various levels of need, right? From like global scale to various kinds of collective instrumentation. So maybe you're deploying on an airborne campaign, or maybe you're just deploying for one single instrument, right? So we want to be able to take advantage of different kinds of encoder complexities, and if there's value add for, say, using one of these 100 million parameter encoders, then we don't want to limit our kind of framework here to only use simple encoders. So over kind of recent history, we've expanded the capabilities to be able to use vision transformers, convolutional deep belief networks, as well as just regular convolutional networks, and various kinds of self-supervised training. So each of those kinds of models has their own self-supervised techniques. Masked autoencoders and IJEPA are some more popular ones for vision transformers. And then there's Pix Contrast, Pix Pro for CNNs. BYOL is kind of the more common mapping to these Pix Pro, Pix Contrast, but this is just a pixel-wise version of BYOL for CNNs. So we have those that you can train on your own, but then also there's this kind of emerging area of these Earth observation foundation models. And I'll get into that in a bit further in a minute, but there's like hundreds of these kind of exploding, and there's more and more popping up every day. And they're not always being evaluated in ways that make it simple for someone to know which one of these they should be using, and why they should be using them. And so, we have this framework, we have this capability that we know works for these subsets of problems. So we set out to do an evaluation with our group at JPL, and then some folks at the Spatial Informatics Group, which spans a couple of organizations, including USF. And more recently, we added some collaborators from Nomic AI and Johns Hopkins for this effort, as well as University of West Virginia and UC Riverside. Really, we want to ask a couple of questions here. So, these foundation models, I'm going to come back to this slide, but these foundation models have come out in a lot of different places. And the idea is that, this slide is specifically tailored towards vision transformers, but the idea is that these models can be leveraged for many downstream tasks. They're trained on massive amounts of data. And they're basically the claim is that they're ready to use and deploy for, multitudes of problems. They can be used whether you have missing bands. Some of them claim they can interpolate across spectral resolutions, things like that. But we haven't found any literature that directly validates these claims over kind of a robust set of problems or tasks. So with that, we kind of wanted to look at, what are we going to evaluate these encoders in terms of like what are they foundational for? How does that look relative to like classic encoders, right? So like a global scheme for classic encoders could look like, a tree-based structure of smaller models, and when you're over different levels, different areas of the globe, you're looking at different subsets of that tree to do the predictions, right? Multiple models for kind of larger global scale problems. And then with these foundation models, you have single models that, at least in theory and in claim, can do that same task for global or larger swaths of the globe at least. So we want to look at, resource needs comparisons. We want to look at the what does it actually look like? What performance are we getting relative to kind of multiple tasks? Like what kind of multitask acuity do these encoders allow for? Um, what differences do we see in the representational capabilities of the encoder on its own, right? So we have the encoder, we have the output layers that we're attaching at the end. But if the claim is that the encoder is itself foundational, then we should see some pretty strong kind of distinct representational differences coming out of the embedding that the encoder provides as well. And then looking at explainability and different ways to kind of quantify some of those explainability metrics. And then also knowledge transferability. So, can I actually do these same tasks across spectral, spatial, temporal domains? Can I do these tasks, with multiple instruments, all that kind of stuff? How does that work in this domain? As I mentioned, right, there's a repository on GitHub that tracks all of these Earth Foundation model efforts. There's hundreds of them. And so it currently is, and it's only going to get more head exploding to, identify which of these are good for your problem and how you might even start to leverage them. Um, I think this is kind of so this is from our partners at SIG, but these are some important things that, we want to be able to say, yes, these things do that, or maybe not all the time, right? Do these things produce higher quality results? Is there a lower technical barrier? Like, can somebody just load the embeddings into Google Earth Engine and play around with them without having to understand how to train an encoder? Do they actually reduce the local compute needed? All those kinds of things. And yeah, there's lots of claims for lots of these different models, but I know that many of the groups that have put the efforts into training these models don't necessarily have the time or the funding to do the evaluation associated. So, the first step that we wanted to take, and that is currently underway at SIG, is to take some of these benchmark data sets and actually provide a comprehensive set of metrics across the different problems that these benchmark data sets provide, and like 5 of the most popular um, foundation models that we're looking at. So that's just kind of like a housekeeping thing. That's something that, probably should be done so people can look at them, reference, and compare against actual pre-existing benchmark data sets. That's awesome, and definitely a piece that needs to be done, but the benchmark data sets don't always cover all of the things, right? The Earth science domain, the Earth observation domain is huge. It spans many different subdomains and many different non-remote sensing, non-earth science areas use this kind of data. So obviously, there's no benchmark data set that's going to cover all of those things. So we also want to look at them, the evaluations from like our specific use cases, which is kind of where we're coming into this with the wildfire and smoke evaluation and potentially other applications. So in terms of performance, right, we want to look at the different encoder complexity and make sure that they're performing better than much simpler models. And then we want to make that evaluation across many different um uh, geographic domains. And in our case, we want to be looking at also spectral resolution variation, um, uh, different things like that, different kinds of instrumentation being used, all that. So um, we're currently in the process of generating these metrics for all of these encoders that we're looking at. But for this specific use case, we have some folks that generated some high quality fire, smoke, and background pixels for some of these scenes across this Fire XAQ campaign. So as a first look, first pass, how does the encoder perform um, here? So we have these metrics here for the deep belief network, the simple encoder that we've been using as kind of a baseline. We're going to go even simpler. So we're going to look at, what if we just use PCA that explains 99% of the variance, which we've compared against in previous papers, and then take that same evaluation and step up. So convolutional deep belief networks, ResNets, um, vision transformers, and then the pre-trained foundation models, right? And what does the variance of performance look like? This is kind of the most straightforward thing that is being done across kind of lots of evaluation efforts. Like what does the end task performance look like for my specific task? And that's definitely an important piece of it, right? But it also doesn't give us the full picture, right? This is simply a qualitative kind of visualization. So what we're finding, just initial pass, as we move from pixel-based views. So what we're giving as input to the deep belief network is a pixel and its neighborhood. And as we move from pixel-based approaches towards approaches that look at larger spatial domains, which do very well and significantly better than pixel-based approaches for things that have a small number of labels for dense classification, so segmentation, and also do really well kind of looking at spatial relationships across large areas to do things like classification. But what we're finding for this approach where we have dense classification and a high number of labels is that there's maybe a little bit of like smoothing and other effects that are coming into the end result when we have these large spatial areas that weren't there previously when we're using the pixel-based approaches. So even we get these kind of weird, and so the tiling is there that can be fixed. That's not part of the issue here, but um, you can see that like this piece here is a river and it's being classified the same as other areas up here, which are not water bodies. And then here in the clay output, which is itself a vision transformer, there's like these patterns that continue to persist across the output, which is something to do with the position in the larger patch that the vision transformer is seeing. It's applying that to the output and giving us some noise there. And then these are again the simplified version, the PCA, so just visual qualitative evaluation, and then having no encoder at all and just doing the segmentation. So with the pixel-based approaches, even the simplified ones, we get a kind of visual distinction between, so this area here on the right, the zoom in is there's a fire front here. It's somewhat difficult to see, but we do see it here and here relative to like here where we zoom in and here where we zoom in from the approaches that use these larger spatial domains, and we're really not seeing much of a differential in those areas, or very noisy, hard to tell differentials. So yeah, there's still some questions to be answered there, right? We do want to provide quantitative evaluation alongside this kind of first pass qualitative thing, but just a note there. So again, we have the ability to evaluate the end performance. We have just a quick qualitative look at the segmentation of a single scene. We also want to look at the embedding area, and first, just look at kind of more classic approaches, or just doing some sort of manifold mapping of this high dimension space. And in this case, we're mapping the labels that we get and the output to the manifold, and then plotting them here. So in this case, we're using t-SNE here with the embeddings from the deep belief networks. Here we're using t-SNE and the labels with no encoder. And here this is PCA being used as input, and we're plotting the first two components of the PCA. Obviously not apples to apples comparisons, but the idea here is that if the embedding is providing good information, there should be some semblance of organization and structure relative to the labels that we're getting on the output end, right? So this was from a previous work, kind of a large scale validation across many different data sets for our approach. This comes from the current work. So no encoding PCA and DBN, again, the kind of simplest pieces, and we're going to step through these approaches through the various levels of complexity of encoders. But what we have here is the final output labels. So in this case, we just simplified to fire, smoke, and none of the above. And then we have the context-free segmentation of the first layer. So as I mentioned, we have the kind of hierarchical approach in our output. And then we have the context-free segmentation of the second layer. And the kind of visualization here, again, can only tell us so much without looking at things quantitatively, which we'll step through next. But we're able to see that there's, the PCA provides us very compact kind of feature space, likely difficult for the models to be able to kind of sift through the information. All right, we're looking at the same number of samples in all of these. Just in the PCA case, they're kind of shrunken into this small area, excuse me. And then the no encoder and the DBN have similar structures, with all of the fire pixels actually showing up in both cases in this top left corner. It's kind of difficult to see at this resolution. Not a significant change, but there is a bit less mixing kind of that happens in the middle here relative to here. And you get to the number of labels that come out of the second layer, and it's really hard to distinguish, right? So these visualizations point here, they're nice and they provide something, but they don't give you a quantitative picture of what the differences of the embedding spaces are really providing you. So this is where our friends from Nomic come in. So they've been doing some work in the large language model space to tackle a very similar problem. So they want to be able to compare embedding spaces across a lot of these large language models. And, really the embedding space idea maps directly over to our problem. So we found their paper, reached out to them, and we have a ported version of their code to generate some of these same evaluation metrics. But basically what they're doing is they generate adjacency matrices in the embedding space, and then they do kernelization across two or more adjacency matrices to map all of the embedding spaces into a single kind of joint embedding space. And then from there, they're doing some statistical analysis. Um, so the kind of null hypothesis is that uh, if you're representing the same um, point in your embedding space in a similar way, the distance in the joint embedding space should be small, right? So from there, you can generate null distributions. You can look at p-values across the different points in your joint embedding and look at how that null hypothesis holds up, right? Look at, which of the embedding spaces are largely different than the other ones, and do it in a actually statistically quantifiable way. So this is kind of huge, right? It moves us past just looking at the looking at the pretty colors, which is commonly where embedding space evaluations stop, and it allows us to look at, are we actually getting distinct differences across these representations, and does that distinct difference map to a performance increase or decrease on the end of the output layer. And obviously there is some confounding information, right? Type of output layer, all that kind of stuff, training and all that. But um, this at least gives us a path forward, a path to be able to quantify, what we're looking at in the embedding space. Um, um, this this piece, so to wrap it back to kind of how we're approaching this problem, um, our hypothesis at the time, the current time, is that it's not really going to be a single model or two models that we jam all of the different spatial, spectral, temporal data into and get all of these different results. But we're going to have an ecosystem of, again, encoders that provide embeddings for specialized um, instrumentation, and then we have the ability to combine those in ways, use them spatially, spatiotemporally, and so it's really going to be like an ecosystem of models. And with that, we want to be leveraging these kind of frameworks that are coming out that are graph-based for models that are using tensors at their very base. So there's this group out of Goddard that is building this tool called Crest that allows you to, you know, um, define graphs that connects ecosystems of models, whether they're physical models or machine learning models. You can train them jointly, but you can also just use them collectively. So you have a model that consists of smaller models, which is not a new idea, but this graph-based structure not only gives you power to train and predict on these machine learning models simply, but the next level of that I'm interested in is being able to extract information from that like graph level. So we collaborate with JDev and Yulia and Yuzu Chen, who look at a lot of the graph structure and analysis of GNNs, and being able to look at not only what kinds of predictions do we get from these separate instruments, but like what kinds of things can we get from the coupled graph structure of these models at the like systems level that allow for kind of um, higher level interpretations of all this information is also interesting. So just a piece to mention here at the end. But yeah, I think the largest takeaway is that we've put forward this framework that allows us to evaluate for current benchmarks and our problem and our partners' problems, and we're working towards publications and full sets of results for these. But really, I think this area of evaluation of these foundation models and different kinds of encoder complexity for various, especially like specific scientific tasks, really needs to be kind of hammered out. Um, so I would encourage you to identify what that evaluation looks like for your specific domains, before landing on an encoder or foundation model, at least at this point in time. And I will leave it there, I believe, for questions. So thank you all for listening, and yeah.
Thank you. Thank you. If everybody can unmute themselves and give Anik a round of applause. That was a great talk. That was really insightful. I'm especially interested in this a coupled reusable Earth system tensor because we have so I imagine like with remote sensing data you have both, so you have spatio-temporal observations, and each observation, if it can be represented as a tensor, then that presents some interesting challenges because the data become like the data is correlated, at least like what we study, it's weakly correlated. So then simple models which are based on like IID assumption of the observations are just no longer sufficient. So I just wanted to mention that that's one like interesting area that we are working on. But uh, with that, we open the forum to questions to Nick, and there is one already in chat. So this is by Dan Wong. Thank you for your question. And it says, can this model be used to detect fire real time? How long would it take to have the sensors data available and the model to ingest those data and output the fire detection results?
Yeah, so great question. So the currently what we're using is level 1B or orthorectified radiance data for the wildfire and smoke problem. So that information comes to us from the ground. So after downlink, so more of like the near real time, the inference for a full scene is on the order of minutes, so it can definitely be put into operational pipelines um, and used there. Another goal of ours is we have these um, labels that essentially that we've generated. We have these that can be used for analysis on the ground. We have the segmentation capability, and we have generated all these data sets, but also they can be used for training onboard detectors, right? So next generation instrumentation that is similar to the instrumentation that we're currently looking at. We have these labels, we can generate them for new instrumentation. And if the hardware goes up, you can upload models, after the thing has been deployed or in, the subsequent airborne campaign if it's an airborne instrument. So that would be more the like the real time like onboard detection piece. And definitely we're looking at that, but haven't gotten there yet.
Yeah, thank you for your question. Any other questions for Nick?
I have a quick question. So first off, great talk. I really enjoyed it. Second, so for training the data, I saw you were using prescribed burns. Those were all like somewhat larger prescribed burns, right?
So those were naturally or maybe anthropogenically formed wildfires. So one I know was lightning strike. I'm not sure how the other one started, but they weren't prescribed.
Okay.
Mhm.
Would it be useful to have like prescribed a prescribed fire with a bunch of data associated with it, such as like fire perimeters or maybe even fire intensity? Like, would that be useful for training the model?
Um, yeah, so there are like associated fire perimeters that some organizations provide.
Hmm.
The not so much the problem, but to use them for validation is tough because they don't have the same temporal resolution or spatial resolution as some of these instruments. So they're definitely good to use as like a comparison. But when we're getting into these paradigms where we have all of these, like, maybe 30 to 50 scenes within an hour across 10 instruments, it's difficult to leverage them um, here. But definitely fire radiative power, like, it's our goal to be able to provide downstream retrievals aside from fire, no fire, smoke, no smoke. So, having that information is always valuable. And I will say that, supervised training of a model with high quality labels is always going to perform better. Assuming everything, the data is engineered properly and all that. So definitely, quality labels associated with the data will get you good results.
Okay, thank you so much.
Yeah, great question.
Thank you. Are there any other questions from the audience? Okay.
Hi,
if not-
I have a question
Okay.
of the CREST system. Can you go a little bit more detail on how the couple training of the different models go?
I can't. So we're not developing this, so I'm not 100% sure about the details. I can point you to the PI of this work. It has been my goal to make their weekly meetings. Currently, they have a small working example inside of a hydrology model kind of ecosystem with physical models and machine learning models, and they've done some coupled modeling. I'm pretty sure that there's some coupling of like LSTMs at the kind of recurrent node level. That is what they're currently looking at. But past that, I can kind of point you to Craig, and he's a great resource to talk to, I would say.
That's great because I'm from the water sector, and we're talking about contaminants in the stream, and with the limited amount of data, we want to use very different distinct models for different phases of the the fate and transport. And in one of our proposals, basically the one of the PIs said, for you to train all the models together, they have to have a uniformed structure, but that we might not be able to do it with the new training data. And this CREST model will completely revolutionize how we can do things in that space. Thank you so much.
Yeah. Let me put my email in here into the chat. I think it's somewhere on the slide too, but I'll put it there. So just send me an email, and then I can give you Craig's contact info and all that.
Thank you.
Of course.
Thank you. Thank you so much. If there are no other questions, I would just like to say that there's an AG, so a general meeting for ties in December. So if you guys would like to register, I think the registration is open. It's a great opportunity to network and meet people in the research field that is common to our goals with environmental statistics. There'll be great people there, and yeah, that's one announcement I wanted to make. I would like to thank Nick again for this great talk. It will be on YouTube, it will be uploaded on YouTube as well. It will take a little time, about a month, but it will be there. I have to update the YouTube. So there's one previous, the digital twins video pending still that I need to work on editing, but it will be there soon. So please subscribe to our YouTube channel as well if you have missed talk or you want to look at these talks again. And thank you, everybody. I will pause the recording. So